Yeah, how do
Yeah.
I control panel?
I'm the Windows person.
You're a Windows person?
Let me go.
Yeah.
Okay, make it so that.
Oh shoot, this Windows 10.
Okay, maybe they have settings. It's like a simpler setting.
No, fuck. This is the old version. I don't know about the old
They're
one.
trying to force everybody to update Windows 10.
Just wait, try typing updates in the bottom search. Hit the other.
Or maybe in.
Yeah.
Sorry, give us 1 minute.
Yeah, there
Yeah,
you
no
go.
rush.
Oh yeah, this is a new version. Okay.
Make
Okay.
it so that it does not.
Yeah, I do really sorry.
Like.
Oh!
Yes, maybe, advanced.
Okay, maybe we restart now.
They're absolutely trying to force these updates from Windows 10 to Windows 11.
Just fight the bullet and let it automatically.
Is there?
I don't want it to be a surprise to
This
us.
advanced option.
Right, right.
I think anything could surprise the speaker at this point.
Okay, maybe we do the restart now, or
Okay, I am so sorry.
What if the whole thing doesn't work? Windows 11? And we do the update.
No, it,
No, it's just I think it's already something new with version Windows. It's just like some really fast like updates. It takes probably like 2 minutes or something. It's just 6 minutes, but like
it says your organization will restart your device at 1:51. So either we do it now or at 1:51. I will give this will be up to the discretion of the speaker. So Nishad,
You'll know down on the right and see if it's running up around.
no, so this is literally now or, but when you try to do this, it's great. Okay, so Nishad, would you like for the restart to happen now or at 1:51?
That's okay.
You guys should do whatever makes more sense. I mean, I don't mind starting after the restart if it's going to take a couple minutes.
Okay. Yeah, why don't we go ahead and do that, and you will get as much time as you need to finish the content of your talk.
Okay, yeah.
Okay, thank you.
No worries.
So 6 minutes. Okay, it says nominally 6 minutes. It will likely be a bit shorter than that.
Yeah, just do you still want to email me if whenever it's done or rejoin the Zoom room? I don't want
Get
to spend.
ready, get ready.
Yeah.
Who the screen
Cool.
of death?
Yeah, we'll do.
All right. See you guys soon.
All right, see you guys.
if you remember some
I don't think there's well half me to take responsibility all of this stuff in the animator. In the animator.
Maybe you just click the Windows button and restart.
Yeah, that looks better than.
Actually
Yeah.
do it like Audio was off. Okay, for all people who are on Zoom, we're experiencing a technical difficulty where the computer forced a restart. We're 30% of the way there. And we will keep you posted when it's ready. It looks
The last 10% takes 90% of the time.
true, true.
That last 20% takes 80% of the.
Okay.
No, Microsoft's being like very like unpredictable. Like sometimes like, yeah, 30% is actually a
I
lot.
blame it on
My experience
Cornell hardware.
that the first 30% is the hardest. Yeah, oh yeah, it restarts at after 30%. And
Oh, wonderful. It looks like it's worth, it's starting to
Yeah, after
restart.
restart, like,
Okay,
see like numbers like adding really quick.
okay, great.
I don't know if you can block the restart function of Windows. Like Windows is known for like hierarchical control.
And some.
It had a sense of humor when I said, when I tried to change the time. I'm sorry, Dave, I can't.
Oh, that would have been brilliant. I should have just set an hour back. Like set the time to an hour back, so then it would have figured it out. Okay. Ah, pity. Okay. 35%.
Yeah.
98. Okay, we're 98% there. Last 2% might be the longest.
That's the problem with Windows, like, the percentage doesn't make any sense. And go like the last 2%.
Include all over the whole.
Still updating, please keep your pants on.
Kind of the limit of our 30%.
100% there, but still loading.
Like, if you look at a simple example, like following you also like the programs of people to allow you to.
Did you guys finish the update?
All the.
That you get control inside the moment.
The control that, like.
Yeah. For that you could control the size of it, there is a problem, but then you could control what you plan. If there's not our. Yeah, the pool of the overall.
I have a fast few. Computers there. Oh, yeah.
Because there is also. There is loading. That's like. Open to be there.
I encourage the audience to reflect on what the talk title means to them in the meantime. Come on, come on.
We're gonna enter Windows 11 after we. No, it's different.
Okay. Here we go. No, I don't want to switch it from my computer because I want to.
Oh, you're.
Yeah, so. Yes, I am Descartes. All right.
Thanks, therefore she is.
Brilliant. Okay, can you hear me?
Yeah, I can hear you guys. Can you hear me?
Wonderful. Cool, we're back.
Nice.
Good to
Not
see
too
you're
bad.
still here. Okay. All right. Why don't you go ahead and share your screen again?
Yeah.
We just had a restart, so you have to outdo that.
Yeah. Cool. Can you guys see it? Can you see the slides?
Yeah.
All right. Perfect.
Okay.
Yeah.
Take two. All right. We're excited to have Nishad here talking to us about fast simulation of fermions with reconfigurable qubits. Take it away.
Cool. Okay. Well, thank you all for sticking around. Yeah. So, cool. So, okay. So a lot of what I research is essentially like how can we use quantum computers for quantum simulation? And, kind of at the beginning of my PhD, we spent a lot of time thinking about analog computing. So how can we really like use quantum devices as a tool for studying nature, where the type of Hamiltonians we look at are actually the Hamiltonians that are kind of easy for us to generate in the lab. So for example, like the analog dynamics of a Rydberg atom array and some fixed connectivity. For example, adiabatic sweeps to prepare ground states, or things like quenches to look at dynamics. However, one of the kind of exciting frontiers that's really being unlocked by by the fact that we really are starting to be able to build very precisely controllable and large-scale quantum computers is actually quantum simulation for real molecules and materials. And to actually study these types of things, programmability is really central. So just to give you guys a sense of, how much scientific work goes into actually studying real molecules and materials, or I should say more generally, like physically relevant many-body physics problems. Here's kind of a pie chart showing a breakdown of the types of fields that use up the bulk of the compute in the NERSC DOE supercomputer. So while a lot of these calculations aren't necessarily studying strongly interacting quantum physics, you can see that like over 50% of the types of problems that people study are actually ultimately at their core some type of many-body physics problem.
Did you have to go back to 2021 because none of this is being funded anymore?
This is the one that I found. Actually, I haven't updated it. I probably should go ahead and update it. Yeah. I'm not sure actually what. Now I'm sure there's some large chunk that's the AI research as well. Yeah. So at the same time, we've been working on improving our quantum computers. And while the promise of using quantum computers for quantum simulation is very exciting, there is, in practice, some pretty important challenges we need to overcome. So for example, we've made a lot of progress experimentally building qubits that have error rates in the order of 10 to the minus 2 and 10 to the minus 3. And this kind of unlocks this like what we call like the NISQ era. So people have been using these qubits to kind of run simple quantum simulations and kind of test some algorithms at the scale where it's starting to become difficult to reproduce classically. However, to really start and leverage like the full programmability of these devices, we really want to be able to down the road go to error rates of something like 10 to the minus 10 to really run large scale simulations. And for this, we also need to do things like quantum error correction. And so a lot of the work that I've been doing kind of bridges the, spans both quantum simulation and also kind of like quantum architecture and error correction type work. Now, if we think about like, even if we have in the future really large scale quantum computers, how expensive would it be to run different types of algorithms? Some groups have actually done some pretty detailed resource estimates for how expensive these types of calculations would be. And if you actually go ahead and look at something like computing the ground state energy of like a single catalyst, like a medium-sized molecule with on the order of 50 atoms, the resource estimates are a little bit daunting. So, they suggest that it would take, potentially like millions of qubits and potentially weeks of simulation time. And so a lot of the work that I've been doing kind of involves trying to understand what are the sources of overhead that go into these problems, and are there ways of kind of circumventing them and kind of further reducing them. So, there's a variety of things, for example, like how do you map the problem onto quantum hardware? What's the structure of the algorithms that you use? And also ultimately, what's kind of the overhead of QEC that goes into this? And really by kind of thinking about these things all together, so like the architecture, the algorithm, and the applications, we're kind of hoping to ultimately reduce the cost of running these types of algorithms. So that's some kind of motivation for the type of work that I'll be presenting today. And in particular, today, what we're really going to focus on is the problem of how do you actually encode fermions into qubits? How easy or hard is it to actually build a simulation of fermions using a qubit-based quantum computer? And so, as many of you guys know, and also I'll maybe pause and ask if there's any questions here, so feel free to interrupt also. And yeah, any kind of questions on the first few slides of motivation? Okay. Cool. Yeah, and just because I can't really see you guys, just kind of shout out loud, and I will not be offended. Okay, so as all of you know, fermions are particles which, when you exchange them, pick up a -1 sign. Now, when we are working with intrinsically like qubit degrees of freedom, qubits are actually like bosonic particles in the sense that when you kind of switch the state of two qubits, if you just apply a swap gate, the overall wave function just picks up a +1 sign. And so, you know, when you're kind of using one thing to simulate the other, it's really easy to actually simulate qubits using fermions because you can do something simple. Just work with pairs of fermions instead of a single fermion. And now, essentially, when you swap a pair of fermions, the two -1 signs will cancel, and you can effectively reproduce a qubit. However, going in the opposite direction is actually something that, you know, involves quite a bit of challenge. How do you actually use these particles that don't have fermionic statistics to effectively reproduce fermionic statistics? And this problem is going to be the focus of the work today. And in particular, we're going to show that for a very general class of fermionic simulation problems, ultimately the overhead is only going to be O of log n for mapping a fermionic problem onto a qubit problem. Now, this has pretty important implications, actually, for how we go ahead and design future hardware and quantum simulation algorithms. There's actually a variety of really exciting work happening right now in the analog space, working with native fermionic degrees of freedom. And also, you know, kind of inspired by the power of native fermions, people have also been kind of proposing architectures for building, you know, full large-scale fault-tolerant quantum computers with native fermionic statistics. Because if you can work with the degrees of freedom that natively have these statistics, then it should actually reduce the overhead of many relevant simulation algorithms, as we'll also kind of touch on later. And so, you know, a key question for understanding what a large-scale quantum computer would look like is how will we actually simulate fermions at this large scale? Okay, so
Question?
Yeah.
So are you going to directly compare your protocol of encoding fermionic degrees of freedom in qubits to these, you know, fermionic, like natively fermionic quantum computers? Like, will there be a benchmark at some point?
There will be, yeah. So I think hopefully by the time I finish presenting the protocol, you should have a pretty clear sense of how this compares with using something with native fermions. Yeah.
Oh, okay.
Yeah, the like looking ahead, this log n number is really, that's the overhead. So like anything you can do with a fermionic computer, you can do on a regular qubit computer by replacing each operation with log n qubit operations, as you'll kind of see.
Yeah, but suppose there's a log n penalty in scaling up fermionic quantum computers, like due to engineering reasons, then you win, right? Like
But you also win. You also win because we learned it's very difficult to do error correction on fermionic computers.
Yeah, that's right. So definitely building an error-corrected fermionic computer is pretty challenging because you can't store information in the like occupation number. That's something that's hard to store logical information in. And you'll kind of see that all the techniques we're using are really nicely compatible just with like regular qubit error correcting codes as well. Yeah, so this new protocol is definitely easier to make fault tolerant. Yeah. Also in practice, log n is going to be relatively small. So it's like some number that's less than 20 for most reasonable imaginable system sizes. Yeah. Yeah, so there is kind of like almost like a constant factor, like on the order of 20, that we can envision for all reasonable system sizes. Yeah. But yeah, follow up if it's still not clear later. Okay, yeah, good question. Other questions?
You may proceed.
Sorry?
Can you see us now?
I can see you guys, but also I'm like on one screen, so everyone it's like a little tiny.
Yeah, no worries.
Okay, yeah.
We'll jump up and down if we have a question.
Yeah, that's right. Don't hesitate. All right, cool. Okay, so let's now kind of start diving into what does it mean to encode fermions into qubits, and what are some strategies for doing this. So the simplest such encoding is something known as the Jordan-Wigner encoding, which many of you may have seen before. And in the Jordan-Wigner encoding, you essentially replace each fermion creation annihilation operator. So here, for example, like a single annihilation operator with a non-local product of like poly operators. So this is essentially like a lowering operator on the same site times a string of Z operators. And what the string of Z operators really does is it mediates the fermionic statistics. So for example, here, if you look at like this string, this is essentially like AI plus AI dagger acting on this side over here. And this here is also, AI plus AI dagger acting on this side here. And you see these two poly operators effectively anti-commute because they intersect here and the X and the Z actually anti-commute. And so by kind of attaching these long Z strings to each of your X and Y operators, you can generate a set of operators in algebra that has all the same properties as like standard fermionic creation annihilation operators. So hopefully this is like a little bit familiar. If not, now's a great time to jump up and ask a question. And one of the kind of nice properties of the Jordan-Wigner encoding is that if you just want to do like local hopping, so say for example hopping between this site and this site, then actually like the types of terms you care about are like AI dagger, AI plus 1. And in these cases, these long Z strings effectively cancel out. And what you're essentially just left with is some local poly interaction. And so, in the Jordan-Wigner encoding, local fermion hopping is an efficient operation. In contrast, if you're trying to do some non-local hopping or non-local tunneling, say for example, between this site and this site, then when you just kind of plug in this operator transformation, what you get out is, now an operator where only the Z strings only partially cancel, and you actually have to fill in all the space between the two insertion sites with the long Z string. And what this means is that, actually doing non-local fermion tunneling is something that could be expensive. You have to implement a high weight operator in the quantum computer. Okay, so the Jordan-Wigner encoding lets us essentially simulate systems with 1D connectivity very efficiently. Now, there's also another really pretty area of condensed matter physics and quantum information theory, showing how you can actually get fermions in local systems in higher dimension, leveraging long-range entanglement. And so, a lot of these results kind of emerge at the same time as like the original proposals of the Tor code and topological order in the early 2000s. And essentially, there's a variety of papers that show how you can take bosonic matter and at effectively low energies, the low energy quasi-particles of this bosonic matter are excitations that have naturally fermionic statistics. And really the key intuition behind it, which I'll dig into in a sec, is that long-range entanglement can actually mediate the long-range fermionic, kind of mediate these long-range Z strings and the non-local nature of fermionic statistics themselves. And actually the fact that you can use topological order and long-range entanglement to capture local systems of fermions in a higher dimension is also the basis of a variety of state-of-the-art fermion to qubit mappings. So for example, there's this thing called the compact encoding, which allows you to simulate 2D local fermions on a square lattice with relatively low overhead. And also there's a whole family of Weierstrass-Dirac encodings, which can also simulate any kind of fixed connectivity with a couple ancilla qubits and relatively small overhead. And in fact, both of these encodings have been explored recently in experiments, both in the Dreyer group and also in our group, in Misha's group. So these methods work for local models, but one of the kind of themes of today is like, what about general fermionic circuits with potentially non-local operations? So before we get into that, I also want to kind of explain a little bit why long-range entanglement allows you to mediate these kind of Jordan-Wigner string-like operations with a simple illustration. So let's imagine something like the Kitaev model, whose details aren't super important. But one of the things that is important about the Kitaev model is that all of the plaquettes, so okay, here qubits live on the vertices, and all of the plaquettes are essentially stabilizers of the state, which are fixed to have expectation value +1. Okay? And let's say you're trying to now do hopping between two sites I and j. Well, if you were just encoding this using a Jordan-Wigner encoding with some type of snake-like ordering of the modes, then the hopping term from I to j would be a non-local hopping, and it would be connected by some long Jordan-Wigner string that, kind of follows the path of this snake. And so you can use Jordan-Wigner to encode n fermions within qubits, but this requires high-weight operators, as discussed earlier. Now, when you have access to stabilizers, local stabilizers with some 2D pattern, these stabilizers can actually act on the system to effectively shrink the structure of these Jordan-Wigner strings. They kind of allow you to move the Jordan-Wigner strings around in the system. And so by applying stabilizers, you can actually take something like a long Jordan-Wigner string and shrink it down to some local interaction. And indeed, actually, this is exactly the underlying physics for how you can use long-range entanglement and stabilizers of the state to effectively turn long-range Jordan-Wigner strings into something local for a fixed connectivity. Now, there's a catch, and the catch is that you've actually used some of your degrees of freedom to generate these stabilizers. And so ultimately, with these types of encodings, you end up encoding something like n/2 fermions using n qubits, but at the improvement of recovering locality in 2D. Okay, so any questions on how this stuff?
So does the application of this the stabilizers or the plaquettes require you to create the long Jordan-Wigner string in the first place?
That's a great question. Yeah. So we'll actually talk about it in the next slide a little bit. But yeah, preparing the state with all those stabilizers is actually a pretty non-trivial task. And that's also where the long-range entanglement comes in. So you need to do something non-local and long-range in order to prepare all the stabilizers into +1.
No, but
Exactly.
I think in answer to the question, you don't have to do the long string. Once you've done the measurements on the stabilizers and that set them all to +1, then all you have to do is the short string, because it's the hard work was getting the stabilizer state in the first place.
Exactly.
Okay, thank you.
Exactly right. Cool, yeah. So, the hard work here is now actually getting the stabilizers to +1, exactly. So, if you can get all the stabilizers to +1, then you can do 2D fermionic interactions locally, right? So, what we do in this experiment, and actually like a well-known technique for preparing stabilizers all in +1, is actually to use constant depth measurements and feed forward. So in the experiment, what we did was we took Ancilla qubits and used them to actually measure these 6-body Pauli operators that I showed on the last slide. And once we make these measurements themselves are randomly +1 or -1, because ahead of time, when you measure a Pauli operator, it's not in an eigenstate at the beginning, so it could be +1 or -1. But what you can do is essentially do like one step of like decoding, the same way you do in an error correcting code. So you can take all of the -1 stabilizers and apply simple Pauli strings between them in order to flip all the stabilizers from -1 to +1. And so after you do this non-local decoding step, in the end, you're going to have a system where all the stabilizers are deterministically in +1, assuming you have no errors in the system. And so what this really means is that, using measurement and non-local classical feed forward, you can actually prepare the long-range entanglement and the +1 stabilizers in constant time, which means that you can actually establish something like 2D fermionic statistics in constant time. Okay, so any questions on this? Like measurement and feed forward is what we use to get topological order, and it's something we've already been using in the experiment to produce 2D fermionic statistics.
Oh, I guess you're like, sorry, so it's kind of a dumb question because, in error correction, you have the chance that, your corrections are wrong, you create logical error, but here, I guess, logical, quote unquote, logical error doesn't really matter, right? Or does it actually matter?
That's a good question. So there's two types of errors we did worry about in the experiment. One of them are logical errors, where like all the stabilizers are still +1, but you like accidentally created some operator that winds around the system.
Yeah.
Those aren't going to matter much here. They essentially will determine some like
Global
they'll
fermionic.
matter a little bit, but they'll determine whether there's some like flux inserted in the cylinder or not. So it'll affect the background fermionic background a little bit. The errors that we were really worried about here actually were like, what if the measured qubit has an error?
Measurement error.
Yeah, exactly. Then the value of the stabilizer that we infer would be wrong. And that's a problem because then we like, the stabilizers aren't all +1, some of them are -1, and that lowers the fidelity of our fermionic operations. Yeah. And so we actually did kind of carefully measure this and characterize it.
I see, but do you do like order, like just one round of measurement, like constant number, or like, whatever, D round, or like, what's the requirement of measurement to get things like, with high fidelity?
Yeah, good question. So in this work, we did just one round of measurement, and then we used the one round of measurement. And so our fermionic operations didn't have like extremely high fidelity yet. Down the road, what you really want to do is actually protect the measurement with some like error correction. So if you can add some redundancy to the measurement, say for example by doing multiple rounds, or by concatenating with an error correcting code, then that's the right way.
Yeah, but also like I imagine you will use this protocol to actually simulate some like many-body fermionic systems, right? So do you have to like do the error correction and run your simulation like simultaneously, like maybe involve them with some gates and then do a round of stabilizer measurement and do another round of involvement? Like, do you guys have this protocol yet, or are you going to talk about that?
Yeah, so I won't talk about this today because basically for the type of stuff I'm talking about today, what we're going to do down the road is essentially replace each atom here with an error correcting code itself.
Yeah. Okay.
So I think that's kind of the way to scale these things to make them high fidelity.
Okay.
Currently, we're using the system kind of in like physical qubit mode.
You imagine concatenation so that there will be a hexagonal like lattice of logical qubits, and
exactly.
So your measurement is also on logical qubits. So there's a built-in fault tolerance that you can pretty much just assert that your measurement outcome is mostly correct.
Exactly right. Yeah.
I see.
So you're talking about measurements, but I don't think you mentioned, was this implemented on a Rydberg array?
This was implemented on a Rydberg array, yeah. So this part, like step 1, step 2, we did in like a recent experiment in Misha's group, like Everett et al. This reference.
Great.
We did this we've done the measurement and feed forward in the system, and it's also kind of a key capability for actually doing quantum error correction at scale. So like pretty much all state-of-the-art quantum computers will have like mid-circuit measurement and non-local decoding type feed forward in the future.
Okay.
Yeah, good question. Okay, so the key takeaway of the last 2 slides are long-range entanglement is important for mediating fermionic statistics, and long-range entanglement, certain types of long-range entanglement can be efficiently prepared using measurement and feed-forward. And so what we did in this work was essentially kind of taking these 2 observations. We were like, okay, what if we are interested in simulating fermionic systems with arbitrary connectivity? And so we developed an approach where we can actually simulate fermionic systems with arbitrary connectivity. And really one of the key insights is we should be dynamically changing the encoding over time. So instead of just fixing something like a single Kitaev model type encoding, let's work with an encoding that depends on this underlying circuit structure that's dynamically changing over the course of the computation. So for example, let's say here we have some arbitrary fermionic circuit, where now each line you can think of as some fermionic mode. And then each kind of, this symbol here essentially represents like a tunneling gate. And these tunneling gates could be non-local. This is essentially a model for a native fermionic quantum computer with all-to-all connectivity. So you'll also kind of see at each layer of the system, at each layer of the circuit, every qubit can be involved in at most 1 gate. This quantum computer can also interact, non-Gaussian, can also implement non-Gaussian interactions. So for example, like density-density, by pairing also long range. And the protocol that we developed was a direct algorithm for mapping an arbitrary fermionic circuit to an analogous qubit circuit. And the key kind of technical innovation that we came up with was an operation that I'll explain over the course of the next few slides called fermionic permutation, which allows you to essentially change the ordering of fermionic modes while kind of capturing the fermionic statistics efficiently. And in particular, we came up with a very efficient way of doing fermionic permutation using only O of log n depth on a quantum computer. And what's nice about this fermionic permutation now is that it allows you to switch the ordering of the modes such that at every single step of the computation, these long-range tunneling gates are forced to be local. So, here you have long-range tunneling gates at every single step. And by inserting these permutations, we ensure that these turn into local gates, during the first layer and the second layer. And because we can make these local, all we actually have to do is use the Jordan-Wigner encoding. So now the Jordan-Wigner encoding plus this fermionic permutation is actually sufficient to implement an arbitrary fermionic circuit in qubits now. Because as you guys remember, Jordan-Wigner is already sufficient for implementing local interactions efficiently.
Question?
Yeah.
So this is like a one-dimensional kind of architecture.
Yeah.
But you just talk about how to do this in 2-dimension with, like the Sirach first Strada kind of encoding in 2 dimensions.
Yeah.
Utilize that in the future, or like are you gonna talk about this?
Yeah, so I think what I want you to take away from the 2D thing is that these 2D encodings actually are 1D encodings with additional long-range entanglement. So like you have the Jordan-Wigner encoding, but then the long-range entanglement allows you to turn the Jordan-Wigner string into something local.
So in the actual like hardware, like quantum computer, are you just gonna snake everything, or
So on the actual quantum computer, we're only ever gonna need the Jordan-Wigner encoding. So like essentially we're gonna come up with circuits that allow you to directly compress these Jordan-Wigner strings from long high weight operators to low weight operators. So you don't have to use a 2D encoding. You can kind of just use Jordan-Wigner plus a fermionic permutation operation.
Okay.
Yeah, good question.
I also have a question. So in the figure where you show how you can use the fermionic permutation to make the gates local, I noticed that the density-density interaction gates are still not local. Is that of note? Yeah, good question. So it turns out that even in Jordan-Wigner, density-density interactions map onto local Pauli operations. So you don't need to do extra work to make the density-density local. In essence, actually, a density-density interaction is really just like the same for fermions and qubits. Okay. Yeah. And if you kind of think about it, if you plug in the Jordan-Wigner strings, the Z's cancel out for the N. Yep. Yeah, exactly. So good question.
Do I understand correctly that in response to the previous question, your fermionic permutation circuits, these order log n circuits, are going to be compatible with this methodology of using the long-range entanglement via stabilizers and keep your strings away?
That's right. Yeah. So like in some sense, what we essentially did was we took the entire procedure of establish long-range entanglement, do an operation, and then remove long-range entanglement, and we compressed that into this fermionic permutation. So that's kind of that's the connection between the two things. We're taking long-range Jordan-Wigner strings, mapping them onto local operations, and then down the road we can undo that. So that's kind of the connection. It's compatible, and it's a dynamical. It's kind of more. It's a more time-dependent way of viewing a similar process. Yeah. Under the hood, though, it is going to look pretty different, actually. So you'll kind of see the circuits in a second. It'll look a little different.
Good, go ahead.
Okay, yeah. Okay, cool. So, we're kind of now trying to work in this dynamical approach where we're directly mapping from like one configuration of Jordan-Wigner strings to another. So we're like changing the connectivity of the modes. And so this actually procedure has been discussed in literature before under the name of like fermionic swap networks. So let's imagine you have some fermionic modes encoded in Jordan-Wigner, and then you want to permute them around so that you have a new ordering. There's a simple rule for how to make sure Jordan-Wigner strings are transformed correctly, which is like apply a CZ gate anytime two modes cross. And this actually makes a lot of sense because if the two modes are both occupied with fermions and they cross, you need to multiply by a -1 sign. That's exactly what a CZ gate does. And if you kind of follow along how Pauli operators propagate through this type of thing, you see that a long Jordan-Wigner string, say with like Z's all the way up till here, and then an X here, essentially transforms into like the Jordan-Wigner string now with a much smaller number of these. Similarly, a shorter Jordan-Wigner string transforms into a longer Jordan-Wigner string once you conjugate it by these CZ circuits. And so by applying these CZs, all the Jordan-Wigner operators nicely map from before to after, and this kind of ensures that the encoding works as expected. However, what's the catch? Well, the catch is that like when you do this permutation, in general, there's going to be order n squared crossings. And so this circuit is actually kind of inefficient. It requires order n squared CZ gates. But I promise you guys only log n overhead. This would be order n overhead. So we're going to find a better way of doing this. So in order to find a better way of doing this, our procedure you guys have to kind of like, there's like two things that I like to get across. So first is that there's a class of permutations that we identified, where we can actually do the fermionic permutation using only O of n gates. So only O of 1 overhead, or order 1 gate per qubit. And the kind of most interesting one is this thing called the interleave, where you take your fermionic modes, you group them into say A and B, and then ultimately the operation that it implements is like a riffle shuffle. So like all of the modes in A and all the modes in B are going to be like interleaved or riffled together, but the order within the groups is not going to change, if that makes sense. And so you can kind of think about this as like two decks of cards, and the order of the left half and the order of the right half are of course going to be the same after you do the shuffle, and the degree of freedom that you have is like how do you insert them inside each other. So one thing I'm going to claim is that this is an operation I can do efficiently with O of 1 overhead. The second thing I'm going to claim is that if you can do this interleave, then you can apply an arbitrary permutation with log n interleaves. And to kind of see this, you can notice an equivalence, and this is like pretty technical, so like bear with me and ask questions. But to kind of understand this, you can notice that there is an equivalence between sorting and actually implementing a permutation. So let's imagine like we take the modes and we number them based on where we want them to go. So what's the target output? Then we can actually use something like a merge sort algorithm to essentially recursively solve the sorting problem. So, first we'll kind of sort modes in like groups of 2, so that 1 and 3 are they're in the wrong order, so we'll swap them, and 8 and 4 are in the wrong order, so we'll swap them, but 5 and 6 are in the right order. And now that you've already sorted kind of in groups of 2, at the next layer you can sort in groups of 4, and in particular you're guaranteed that the left 2 will no longer need to cross, and the right 2 will no longer need to cross. And so this actually exactly corresponds to permutations that match this interleave structure, because the left half and the right half are going to have like no more crossings. They're going to be 2 groups that have the same order before and after. And so once you do that now in groups of 4, at the last step you do it also in a group of 8. And again, because you've already pre-sorted the left and the right, the final operation doesn't involve any more crossings with the left and the right. Yeah. And so each one of these operations is actually exactly of this interleave type. And for those of you who are kind of familiar with merge sort, this is actually exactly also how the merge sort algorithm works in computer science.
Okay.
Cool.
So you're not claiming this is a new result. This was already well known in the CS and math literature.
100%, yeah.
Great.
Yeah, this,
Yes. No, the application for the log depth of the circuit is great.
yeah. Yeah, it's actually, I think, like, I think I learned this in my, like, first intro CS lecture my freshman year. Yeah. It's pretty foundational. It's awesome. Yeah, so we can do now you would log n interleaves an arbitrary permutation. So now comes the harder part, which is how do we actually do the interleave in order 1 depth? And so I'm going to kind of break it down, but here's essentially like the key circuit that we're going to use to do the interleave in O1 depth. And so these are the modes that are like group A, like left, and these are the modes that are group B, right? And as you can kind of see here, like what I've depicted is a particular interleave operation where the left half and the right half like kind of cross. And so what the circuit is going to involve is like, first in group B, we're going to run a C0 cascade. This is essentially a staircase type circuit where like, you have control, target, control, target, control, target. And the idea of this circuit is that it's going to essentially propagate information non-locally within group B. And these things are really going to, at some level, actually like compress the complexity of the fermionic swap network. So by propagating information non-locally, they're going to make the fermionic swap network much easier to implement. Now, once we've done this compression step, then the CZ gates that we need to generate the fermionic statistics actually become much simpler. In particular, for every single mode in A on the blue qubits, we simply find the closest mode in B to its left and apply a CZ gate between them. And then finally, we actually kind of undo the circuit and now run like a decompress, and then finally put all the modes in the position that we actually want. So this is kind of like the procedure. And if you kind of notice, each layer here involves like order 1 gates per qubit. So the total number of Clifford gates of this procedure is actually O of n, which is already actually an order of n less than just using only CZ gates on its own. Now, the next thing I kind of want to point out is that while the C0 ladder propagates information non-locally, so if we're kind of doing it in this using local operations, inevitably this will come with some like depth overhead. However, it turns out that using measurements and feed-forward, you can actually implement the C0 cascade efficiently just using a depth 2 circuit measurement, and then classical feed-forward, kind of illustrated here. And this is actually also not a new result. This is also widely known. But what's kind of key here that I want to point out is that the classical computer is actually doing a depth n calculation. So the classical computer actually has to kind of aggregate information across all the measurements and propagate them in a non-local way to do the feedback. But what's nice is that from the point of view of the quantum computer, this is like a constant depth circuit. There's also turns out to be versions of the C0 ladder that can be done without ancillas and log n depth. In particular, there's like this kind of nice result from CS. And also this result was applied to kind of extend our techniques in this recent paper as well. Okay, so now we have the circuit structure. Yeah, sorry.
Are you worried about the error propagation among your entire protocol? Because like you're shrinking a very high weight poly operator that's potentially meaningful for a calculation.
Yeah.
Right. So when they're doing these cascades of like, C0 gates, errors are certainly going to be propagated very, very, very non-locally, right? So have you guys done any simulation of your protocol? I guess because I'm worried that, this is going to cause errors to propagate without control.
Yeah, so maybe what I'll say is that like, I think down the road, we would really want to use this protocol with error correcting codes.
Yeah, I know.
Where you
Even
kind
with
of-
error correcting code, like on the level of logical qubits, there will be logical errors propagating on like this very long like range of or the neural system, right? So
Yeah, but if we're using an error correcting code with like moderate distance, I'm actually not too worried about that because all of these are Clifford operations and they're actually like really efficient. Because and actually like, I mean, maybe one other comment I'll make is like there's another kind of thing that we've also been working on in Misha's group has been like understanding how to do Clifford circuits with poly initialization and poly measurement in the error corrected setting.
I know this like algorithmic fault tolerant story, but
That's right.
you think that would essentially, you know, ensure us that this error propagation, like in whatever circuit that implements, is going to be not a big problem?
That's right. Yeah.
Okay.
So like in the error corrected setting, we'll get this exponential suppression with D, and like the propagation here will be like no worse than like, you know, N.
Right.
So
Given that all of those stuff,
yeah, we expect the areas here will probably grow linearly with the number of measurement sites.
okay.
Yeah, which is as good as you can hope for. I think also maybe it's worth thinking through, like just for context, if you were directly going to implement the high weight poly operator, that would also have error that grows as N. So from the error propagation point of view, it's not surprising that you have error weight that grows with the distance between two modes.
Okay. Cool.
Yeah, good question. Okay, yeah, so here's the circuit involving these multiple steps, and then also the kind of fact that you can implement a CNOT ladder with constant depth. Now, next, let me kind of tell you how does this procedure actually reproduce a fermionic swap network. So I'm going to kind of go in two steps. So first, let's take the circuit and actually just redraw it. So now we think about just directly like the CNOT circuit conjugating the CZ circuit. So if you kind of I've moved the CNOTs now through the permutation, so you can actually kind of see which modes each of the CNOTs are acting on. So you'll see the CNOTs only act on the green qubits, essentially, down here. And so the core structure here is some CZ circuit conjugated by a tower of CNOTs. Yeah. Okay, and there's essentially a pretty simple circuit identity we're going to use. So what you see is that if you take a C, and we can look down here for the circuit identity. If you take a CZ gate and you conjugate it by a CNOT gate with the target on one end of the CZ, then what this essentially does is it copies the CZ onto the target back here. And so now you like take the CNOT and it turns one CZ gate into two. So this is essentially like a simple circuit identity. So when you now take a CZ gate, like let's look at this one up here, and maybe I'll circle it actually just for, let's look at this gate here. And you conjugate it by this tower of CNOT gates. At each step, you're essentially taking the CZ gate and copying it over one more. And so what you kind of end up generating by conjugating the CZ gate with the CNOT ladder is a large collection of CZ gates that looks like this. And in particular, you'll notice that this CZ gate involves like coupling this mode here to all of the green modes here. And so you kind of captured all of the crossings as this mode has moved to the left, as this mode moved to the right, if that makes sense. Okay, so does that kind of make sense, how we were able to do the transformation for one CZ gate? Okay, silence is either yes or everyone no. Okay, cool. Yeah, okay, nice. And then what's kind of remarkable about this circuit is that using the same CNOT ladder, you can essentially do this broadcasting of the CZ gate in parallel for all of the gates in this layer. So now, for example, let's say we like fixate on this gate. This gate will also now be broadcasted to all of the green qubits on its left as well. And so now this kind of captures all of these crossings. And so you kind of see all of the crossings associated with one line in the circuit gets mapped onto one CZ gate using the same CNOT ladder for all of the gates in the system. And so effectively, this is how we managed to compress these O of n squared CZ gates into O of n total gates. So like O of n CNOT gates and O of n CZ gates. Yeah. And that's kind of like the core actually technique for how you're able to do this. You're able to kind of, using these permutations with very special structure, compress. It's essentially at its core a Clifford compression method. All right, cool. So that's kind of like the core technical result. And now everything else I'll kind of explain is like generalizations and applications. So yeah, and okay, now we'll pause again if there's any questions on the core technical result.
Just another like maybe physical level question, which is, do you actually need to do like physical swap gates, or you just
Good question. So I think this makes the most sense in platforms with non-local connectivity. Because if you had to do physical swap gates, then you'd end up doing O of n squared swap gates.
yeah. So okay, I see. Yeah, this is for reprograms. Okay, sure.
Exactly. That's why we started thinking about this. But then also for things like ions, anything with, or even photons.
Yeah, because
non-local connectivity.
Yeah, because I would imagine if you do this for transmont, you cannot avoid this penalty.
That's
Like,
right.
You're avoiding this penalty because of your flexibility and connectivity. Okay.
Exactly. Yeah, so we're like kind of working in a limit where like non-local swaps are free.
Okay, cool. Thank you.
Yeah, good question. Okay, cool. So as you guys kind of saw, the core structure we were using was like, we found this class of permutations, the interleave, and then we constructed this like C0 circuit conjugating some CZ gates in order to implement this interleave efficiently with, order 1 overhead per qubit. It turns out that the interleave is not unique. There's actually a whole variety of efficient permutations that have enough structure that this type of circuit compression is possible. So in particular, we also like found that 1D reflection and 2D reflection are both operations that are kind of efficient. We also found in general that you can like take any O of 1 permutation and deform it by kind of deleting modes or duplicating modes, and this doesn't fundamentally change the complexity of implementing these permutations. And so we actually don't think this is an exhaustive list at all. And there's a whole family of like kind of structured permutations that can be done with actually constant overhead. And here by constant overhead, it really means like, some multiplicative constant compared to some native fermionic processor with non-local degrees of freedom. Yeah. And what's kind of neat about this large toolbox is that it's actually useful for designing fermionic quantum algorithms. So even though we have this worst case result with log n overhead, in practice, it might also be interesting to design algorithms that use these O of 1 overhead operations. Okay, so with that, we're kind of entering the last part of the talk. And in particular, I'll kind of go through 2 applications. So the first application that we thought through was applying this technique to simulating sparse SYK models. So as you guys may have heard, SYK models are like basically random models with 4 Majorana interactions. And these are kind of like, highly non-local in general. And there's also these particular sparse versions of the problem where each mode has constant degree. And so we can efficiently compile sparse SYK into some Hamiltonian simulation algorithm, leveraging the fact that we can implement arbitrary permutations to compile like any random Hamiltonian. And what this kind of looks like is alternating between these like fermionic permutations and some local ZZ interactions. And we did some numerics to estimate what the cost would be. And so we kind of like compare 3 things. The orange dots correspond to what the cost would be if we're using like swap networks. So basically like just prior state of the art. The black one is what it would look like if we're using kind of our compiled permutation. This is like the log n result. And you can already kind of see like a speed up of like, somewhere between 5 and 10 for going from swap network to compiled permutation. However, then we also kind of asked, well, what if the interleave is sufficient for generating randomness itself? Like if we just alternate interleave ZZ gate, interleave ZZ gate, does that generate a sparse SYK ensemble that is also chaotic? And our numerics, we didn't really study this deeply theoretically, but our kind of like preliminary numerics suggested yes. So, this could actually be also a potentially interesting direction for like continued future work. Are the types of structures that enable constant depth compilation sufficient for capturing the properties of SYK that people care about? And if you can do that, then you could even achieve like another kind of 10x speed up by using the most efficient fermionic simulation approach. Okay, so the next kind of type of application that we were very excited about is simulation of materials. So let's imagine now we have some periodic translationally invariant material, but with some like non-local, potentially complicated hopping structure. One way of dealing with this non-local hopping structure is to actually use a fermionic fast Fourier transform on the quantum computer. And in particular, I'll show you how we can do the fermionic fast Fourier transform in log n depth. And this really unlocks fast algorithms for both preparing generic states and also doing Hamiltonian simulation. And our kind of new results actually unlock an implementation of the fermionic fast Fourier transform with significantly lower overhead. So the prior results kind of involved some depth that's scaled with system size, but now we can kind of show that you can do the fast Fourier transform just in log depth, which saturates the complexity of doing it with like native fermionic degrees of freedom. And the key idea is that when you're doing a Fourier transform between fermionic modes, the purpose of this Fourier transform is essentially to transform your creation and annihilation operators from real space to momentum space. And the type of circuit connectivity that you need is essentially the connectivity of a hypercube. So at each layer, you need to couple modes non-locally with some distance that grows as powers of 2. So at the first layer, it's like nearest neighbor, then next layer, it's distance 2, then distance 4, then distance 8, and so on. And the fact that you have this like kind of regular structure means that we can actually do this very efficiently just using interleaves. And so the structure of the fast Fourier transform very nicely maps onto the interleave. So this is kind of the first example of some fermionic simulation algorithm that can be co-designed with this O of 1 overhead toolbox. You can also generally do this in higher dimensions, also using reflections. So now if you think about your fermionic modes, everything's still encoded in Jordan-Wigner, but you can do Fourier transforms on rows, do a reflection, and then do Fourier transforms in columns. And this allows you to transform your fermionic creation annihilation operators to 2D momentum space. And also all of this happening with constant overhead. And what's really cool about being able to switch between momentum space and real space on a quantum computer is that it's actually something that we use in theoretical condensed matter all the time to help us make sense of these systems. And that's because oftentimes things are much simpler in momentum space. So for example, let's say we're trying to prepare some pretty complicated states like a P-wave superconductor, some gapless critical point, a Fermi surface, a chiral topological insulator. If we could transform to momentum space, then all of these states can be prepared with constant depth circuits. Things that just involve coupling some small number of K modes. So for example, you do some local interaction if you have a 2-site unit cell in order to prepare something like the critical point of a honeycomb of a hexagonal lattice state. And you can do this in momentum space and then using this efficient log depth operation, transform into real space as a way of preparing this state more efficiently in your quantum computer. There's also actually a huge family of phases of matter that can be built by combining these complicated free fermion states with things that have topological order. So for example, if you have a P-wave superconductor and a toricode, then you can actually interleave them in order to get out a chiral spin liquid. So there's this, you can kind of think about this now as a new building block for state preparation. And now there's a large family of pretty exotic states that with this non-local connectivity can really be prepared with a very small depth that grows very slowly with system size, log L. Okay, and since we're running short on time, maybe I'll pause actually for questions. So any questions on the state preparation stuff?
Yeah, I'm just a little perplexed when you talk about this fermionic fast Fourier transform. Is that fast Fourier transform, in the technical sense of what we mean by FFT classically?
It is. It is kind of analogous.
I thought that was hard to do, bosonically, and so is the statement is that it's somehow even easier fermionically?
Yeah, okay, yeah, sorry. So I think I should have actually explained this. That's a good question. I forgot to explain this. Good question. So there's the type of Fourier transform that I'm talking about here is when you kind of define new degrees of freedom. that are like Fourier transforms of the original operators, like this type, where these are all operators. And so this Fourier transform is something where like each qubit kind of acts like 1 degree of freedom because it supports one fermionic mode. And so now the butterfly structure associated with the fermionic, like the FFT, when you think about it in terms of matrices, gets reflected as like a butterfly structure in the connectivity of the qubits. And so indeed, what I am saying is that this Fourier transform with the FFFT is really easy to do using our new techniques.
Great.
This is very different actually from like the Fourier transform where I have like a bunch of modes and I want to like compute sums of the densities on a bunch of modes. And this is like the type of Fourier transform that you would have to use in some quantum algorithms. And this would be like a classical Fourier transform because you're essentially doing like arithmetic on your quantum computer. And that's a different one actually. And that one that turns out to also be quite a bit harder.
Good.
Yeah. Good question.
Maybe can you stay on this slide? So,
Yeah.
So sorry to bother about the fault tolerance again, but it seems like
no,
you're having a lot of phase gates that are non-Clifford in this context in the
Yeah.
Yeah. So do you have any plan to actually carry them out fault tolerantly?
Yeah. Good question. I do actually. So I also love thinking about things fault tolerantly. So I'm also happy to talk about this a little bit more afterwards because it's a little technical. But I actually spent a lot of time thinking about what's the best way of compiling this into a Clifford plus T gate set.
Yeah.
Because that's really what we want to do if you want to use this fault tolerantly. And it turns out actually that the phases that you use in the fast Fourier transform also have a lot of structure.
It's always
in particular,
like root of T, right?
Yeah, exactly right. So it's always like power. So for example, if you're working on a system with like 16 or 32, some power of 2, then these rotations are always like roots of 2. And there turn out to be some pretty efficient fault tolerant circuits for synthesizing these operations in parallel. So if you're like trying to synthesize each one separately, that gets really expensive because you have to use a Hadamard T synthesis to generate a small angle rotation. But if you have now many of these gates and you try to just synthesize all of them in parallel, you can actually use some circuits with ancillas and these things called catalyst states to actually generate all of these T's in parallel using something that asymptotically is equivalent to like 1 Toffoli per T gate.
I see.
1 Toffoli per phase gate. Sorry, 1 Toffoli per phase gate. Yeah. And so what's nice about the fact that you have like 1 Toffoli per phase gate is that now the T count of the circuit is also like n log n, or like the Toffoli count is n log n. And so now in our new compilation, like the Toffoli count is n log n and the Clifford count is n log n. And I did some estimates for like n equals 256. And so ultimately this circuit actually now uses 50 times more Cliffords than T's. Which is interesting because I think it means that like the cost of the circuit might not be bottlenecked by the T's.
Oh, I see.
Yeah.
I see.
Yeah.
More offline. This is too technical for general.
Yeah, happy to chat more about this. But yeah, it's a good question how to actually do these things fault tolerantly. Cool. Okay, nice. Any other questions? Okay, so the last thing that I'll also kind of flash is that also this FFFT is a really powerful tool for Hamiltonian simulation of generic translation invariant Hubbard models. And so, this is actually a pretty important model both for chemistry and materials. And a Hubbard model with translation invariance, but potentially long-range hopping, and also kind of translation invariant, but potentially long-range density-density interactions. And, our new result shows how you can do the kinetic term in n log n with O of n log n gates by directly diagonalizing the kinetic part. And the interaction in diagonal terms, they're already diagonal, so in some sense they're easy. But actually, in general, there's O of n squared such interaction terms. And some papers have kind of showed that asymptotically, the best way to implement the interaction terms is actually using this classical Fourier transform that I just mentioned. And this kind of has now some like polylog n multiplicative overhead if you're using classical Fourier transform. So kind of the thing that I just want to highlight here is that the bottleneck of this procedure used to be the kinetic term, because the kinetic term used to require O of n squared gates. But now with this kind of reduction, this translation invariant generic Hubbard model simulation procedure is a little bit more realistic in the sense that asymptotically now it just uses something that's like nearly constant depth and like nearly linear space-time overhead per query. Yeah, so this is like much easier to do now. Cool. And with that, I'll maybe like have one quick kind of outlook. So something that I'm also very excited about is co-designing these fermionic simulation procedures with hardware and error correcting codes. And so, you know, we talked about this FFFT quite extensively. It has the connectivity of a hypercube. And actually in neutral atoms, these circuits with hypercube connectivity are actually really natural for us to do. So you've already kind of been using these to simulate 832 and 1642 error correcting codes in the system. Also, you know, one thing that's particularly interesting is, can we kind of now combine the design of our circuit structure with the design of the error correcting code itself, in particular when you're thinking about LDPC codes. And so also like a new result that we've recently put out is essentially a toolbox for doing parallel quantum circuits efficiently with LDPC codes. And these kind of parallel circuits involve many repetitive components. And we showed that if you have many repetitive components, you can actually share the cost of error correction efficiently among the various components to reduce the overall asymptotic cost of the simulation. So I think both understanding how to integrate both hardware constraints and also constraints coming from error correction with the types of circuits that this procedure generates could be an interesting direction for continued future work. All right, and with that, I want to thank all of my amazing collaborators on this project, and thank you all for your attention.
Thank you so much for the wonderful talk. Do we have any questions? Well, maybe before the technical questions, do we have any more general questions?
Just one general, you know, I asked earlier and you said you had implemented that 2D with the stabilizers on a Rydberg atom array. How close are you to implementing any of the fermionic, you know, interleaf permutations?
That's a good question. We've started kind of thinking about it and planning it. Hopefully, in the next year, we'll have some demonstrations of this. Yeah. I think the big outstanding question actually is like related to some of the questions we had during the talk today, which is like, how bad is the error propagation in practice? And for near term, is this a reasonable way of doing it? Or do we need to wait till we do it with fault tolerant qubits? I think that's kind of the outstanding question at the moment.
So, and this you're still doing in collaboration with Misha's group at Harvard?
Yes, we've started talking with Misha's group about potentially running those things. Yeah. It's quite early stage right now, and we're still trying to think about what also the best application would be for the near-term experiments.
Good.
Yeah, good question. Thanks.
Any more questions? Okay, if not, let's thank our speaker again.
Really good.
All right. Yeah, that was a phenomenal talk. Thank you for being patient with our computer difficulties.
Yeah, of course. Yeah, thanks for the invitation. And I think the computer difficulties didn't end up being so bad. So, yeah.
Well, yeah, have a great rest of the day. I'm looking forward to.
Cool. Yeah. Thanks again. Bye, everybody.